All right, so we're very happy to have Jan Baruch from Berkeley, and he will tell us about some upcoming work about the ultralocal measure. So go ahead.
Thank you very much. Thank you for inviting me. I'm really happy to be here. Today I'm going to be talking about the functional measures for one-loop computations. And this is based on upcoming work in collaboration with Maciek Kolanowski and Don Marolf. So let me start with the general motivation and how we started thinking about the subject. So one of the biggest successes of the gravitational path integral approaches to quantum gravity in recent years was the computation of the supersymmetric index in supergravity and reproducing exactly the microscopic supersymmetric index through explicit sum over geometries. This is done by performing a localization computation in the near horizon Frog region of ADS2 crosses 2. And then summing over all possible geometries consistent with those boundary conditions. Now, this is a very nice setup to be in, because through this one could hope to develop essentially a higher dimensional toy model for testing the rules of the gravitational path integral. However, before moving further and trying to perform similar computations in setups with that are slightly more complicated, so for example, supergravity theories with lower number of supersymmetries, one has to address several puzzles that have been pointed out by Ashok Sen in a paper 3 years ago. So one of such puzzles is related to the problem of the computation of one-loop determinants in these localization computations. So when we perform these localization computations, we're essentially summing over all possible over all saddle points that our path integral localizes onto, together with their one-loop determinants. Now, to compute the index, naturally we're computing these path integrals with supersymmetric boundary conditions. However, it turns out that now when we try to compute the one-loop determinants, the one-loop determinants are the supersymmetric saddle points. It turns out that the space of normalizable fluctuations that we integrate over to compute these one-loop determinants is actually not preserved under supersymmetry. So more precisely, what happens is that if we take a normalizable mode with respect to some chosen linear product, and then act with a supersymmetry transformation, we end up with a non-normalizable mode. So what this essentially means is that the computation itself is has some holes in it, and it's hard to say what are we actually computing. And if one looks a bit further in the literature, it turns out that this problem is actually universal when performing localization computations in ADS spacetimes. So even without the complicated context of the gravitational path integral, if one tries to perform localization computations, for example, in gauge theories, in anti-de Sitter spacetimes, one would also run into a similar issue. So it turns out that this issue of normalizability of these one-loop fluctuations is actually related to other puzzles about ultralocal inner product that's typically used in computing one-loop determinants. So today I'll discuss the relation to these other issues that one can find when working with ultralocal inner product. Then we'll try to address these issues by returning to canonical quantization. And then I'll explicitly show how, with a modified approach, one can explicitly avoid this puzzle that appears in these supersymmetric setups. So to begin, let me start with the simplest possible setup that we can imagine for computing one-loop determinants, which in our case is going to be a free scalar field in ADS given by this familiar action. And we want to consider a thermal partition function of this free scalar field. Now, formally, what we would usually say when we perform a path integration in this theory is that the resulting partition function would simply be given through the one-loop determinant of the Klein-Gordon operator. This is only a formal statement because we have to actually define what do we mean by this determinant. So in practice, what we do is we introduce the inner product on the space of fields that we want to integrate over. Then we reinterpret the expression that appears in our exponential in terms of this inner product as some operator acting on the Hilbert space of these fields. And then we use the spectral theorem to diagonalize the resulting operator on the space of normalizable fluctuations. So a common choice for performing these computations when it comes to the inner product is the choice of the ultralocal inner product, which is defined simply through this expression. This is a very natural choice because it's manifestly covariant. However, it has some puzzling features in ADS spacetime. So first of all, if one studies the spectrum of the Klein-Gordon operator defined with respect to this inner product, one will find that even in thermal ADS, in Euclidean signature, this Klein-Gordon operator has a continuous spectrum. Furthermore, the Klein-Gordon operator also does not allow for the choice of boundary conditions if we work with this inner product. And lastly, as I'm going to discuss a bit later in the talk, it's actually this choice that leads to the space of fluctuations that's not preserved by supersymmetry.
What do you mean by it does not allow boundary?
Yes, so there's going to be a more precise statement for this later, but essentially the point is that the Klein-Gordon operator is essentially self-adjoint. So the point is that with this choice of the inner product, there's actually no freedom for this operator.
It's already self-adjoint.
Yes, exactly. Yeah.
So in the continuous spectrum, is there any mass?
Yes. So you're asking, sorry, can you repeat the question?
Well, you use a continuous spectrum with Klein-Gordon operators, that's going to depend on the mass.
The spectrum itself, so the spectrum itself will not depend on the mass. The spectrum itself is going to just be labeled by the, sorry, let me be more precise. Yes, the spectrum will depend on the mass. But the point is that for any choice of the mass, you're going to find that the Klein-Gordon operator will have a continuous spectrum. So, So these are these puzzling features of this related to the inner product. So now I'm going to discuss all of these puzzles in a bit more detail. So first of all, let me remind you. Why are we used to thinking of ADS spacetime as a box? And why am I bothered by the fact that we get a continuous spectrum for the Klein-Gordon operator? So this comes from the classical Lorentzian intuition, which is that if we solve the Klein-Gordon equations in ADS background, what's going to happen is that we're going to find that the actual spectrum of the energy levels that we're going to find is discrete. So, for example, for Dirichlet boundary conditions, we're going to find that it's approximately that it takes this form, and importantly, it's only labeled by discrete labels. So this is kind of what something that we're used to when studying quantum mechanics in a box. On the other hand, if we now study the off-shell Euclidean physics defined with respect to the ultralocal inner product, then what we'll want to diagonalize to perform our computations is this Klein-Gordon operator. And now it turns out that this Klein-Gordon operator has the eigenvalue spectrum that is explicitly continuous due to this lambda parameter that can actually be any real number. So essentially, what's important to remember here is that if instead we try to diagonalize the Klein-Gordon operator in the actual box in flat space, we would actually find a discrete spectrum. So it's not something that we would expect to see when diagonalizing the Klein-Gordon operator in a box. So essentially, what it seems like is that our choice of the inner product led us to discover that offshore it looks like there is no box in this computation. Now let me discuss the issue of the boundary conditions. So all allowed boundary conditions classically in ADS spacetimes have been classified by Ishibashi and Wald, and this was based essentially on the requirement that whatever boundary conditions we choose for our fields, they lead to a stable classical time evolution in the bulk. And what they found through their analysis is that for large enough values of the mass, so for this parameter no greater than 1, one is only allowed to impose Dirichlet boundary conditions on the fields. However, in this so-called BF window, so for small enough masses, one is actually allowed to choose different boundary conditions, and there is a full one-parameter family of allowed boundary conditions that one can impose. Let us compare this now with what we find for offshore physics with respect to this ultralocal linear product. So let me define this functional space of normalizable modes by just all possible field configurations such that the ultralocal linear product is finite. Now, if we assume some asymptotic decay of these scalar fields as z to the delta, we're going to find through a simple computation that this implies that asymptotically delta, that this asymptotic decay is only normalizable as long as delta is greater than d over 2. So essentially what we find is that we can only in this region we're essentially allowed to study classical physics. So here I want to emphasize something. So here this delta, I just denoted arbitrary decay of any field. So this delta is not necessarily related to the mass. But the logic, however, is that we find that the classical fields, which would asymptotically have decays that would be in this region, they do not belong to the functional space defined with respect to the ultralocal inner product. So in other words, these onshore configurations with Neumann and mixed boundary conditions are not part of the functional integration space, and therefore we are not really allowed to study the classical physics with these boundary conditions if we work with this inner product. So this is essentially a way to see that the ultralocal measure only allows us to study Dirichlet boundary conditions in ADS. Now, both of these previous aspects were essentially hints that something is off, and now to essentially summarize this with a very precise statement that points to what is the actual issue. I have to remind you a bit about what are the how do we actually define self-adjoint operators. So a general operator A is going to be self-adjoint if it actually satisfies two conditions. One is that it has to be symmetric. This is something that we're all used to. But the other thing that's sometimes forgotten is that the domain of the operator A has to be exactly the same as the domain of the adjoint operator. So now, given a symmetric operator, how do we check whether the domains of that operator and its adjoint match with each other? For this, we can rely on the theorem proven by von Neumann, which relies on investigating the so-called deficiency subspaces n plus and n minus of the operator of interest. So to check whether our operator is truly self-adjoint or not, what we do is we essentially compute these deficiency subspaces, which are defined essentially as subspaces spanned by the fields which are eigenfunctions of this operator with purely imaginary values, and similarly for these deficiency subspaces with the opposite eigenvalue, and then we care about the dimensionality of these subspaces. Then what von Neumann theorem tells us is that the operator A is going to be self-adjoint even only if these dimensionalities of these deficiency subspaces are the same and are zero. So the example of such a situation is in quantum mechanics when we study a momentum operator on the whole real axis. There is no box there, and there's no need to impose any boundary conditions, and correspondingly we also find that the momentum operator is essentially self-adjoint. On the other hand, there are also cases in which the dimensionalities of these deficiency subspaces can be equal but greater than zero. And this is a case in which you essentially find that the operator A is symmetric, is not self-adjoint yet, but it admits self-adjoint extensions. So when this operator admits different self-adjoint extensions, these extensions are classified by the allowed boundary conditions for this that can be imposed for this operator. So an example in quantum mechanics would be precisely momentum operator on a finite interval. So from this we see that essentially to actually see the box in our offshore physics, what we would expect to find is that we should find an operator that's symmetric but not yet self-adjoint, so that it admits different self-adjoint extensions for different choices of boundary conditions. Now, with this theorem, what we can do is we can go to this to the case of this Klein-Gordon operator defined with respect to this ultralocal inner product, and we can now see what is the actual issue. It's possible to show that this Klein-Gordon operator has actually zero-dimensional deficiency subspaces, and therefore it's already essentially self-adjoint, and therefore it essentially behaves like the momentum operator on the real axis. So it actually completely does not see the box, and correspondingly there is no freedom for us to impose different boundary conditions for this for the scalar fields. So now we could ask, is this actually a problem? Maybe what it tells us is that actually the classical analysis is misleading, and we should just actually always study the Dirichlet boundary conditions, which are above this window that I described. However, the answer is actually yes, and this has been known for some time, because there are known ADS-CFT examples of operators whose scaling dimensions exactly lie in this BF window between the unitarity bound and the BF bound. So therefore, there are operators which we explicitly would not be able to study in the bulk in ADS-CFT if we are not able to study this offshore physics directly in the BF window. So therefore, this is a problem for us, and now we're going to try to come up with some other natural choices of the inner products, and see whether they would help us resolve this situation and bring back the match between Lorentzian and Euclidean physics.
I mean, your previous sort of intuitive argument about the delta kind of already established. I mean, do you need the whole von Neumann theorem?
It just like, yes, I mean this I would say that this is already like a very strong hint for this. But the point is that this answers the question, like this whole von Neumann theorem answers for you the question, what do we mean by the fact that there is no possible choices of boundary conditions? But like without that, you would have some trouble, I think, phrasing it kind of more rigorously. Why is it the case that you cannot impose different boundary conditions with respect to the ultralocal inner product?
Right, but although since the fields fall off, I mean, the solutions were already falling off in a way that made them non-normalizable.
That's true. Yeah. Yeah. I agree with this. Okay, so to address this situation, what we propose is to try to return to canonical quantization. So for free fields, they can be treated in KFT as essentially infinite number of decoupled harmonic oscillators. So if canonical quantization is supposed to work for anything, it better work for this case of free fields. So what we're gonna do is we simply consider the Lorentzian action for this free scalar field on some generic curved background. Here for simplicity, we focused on static backgrounds, but the analysis also would hold for stationary backgrounds. Now, computing the conjugate momenta, we find this simple expression. Here, this H is simply the spatial part of the metric, and N I will refer to as lapse. And correspondingly, now the Hamiltonian obtained for this theory takes this form. So now let us consider a thermal partition function with simply computed by the trace of this canonically quantized Hilbert space with this canonically quantized Hamiltonian H. Performing the usual kind of first quantum mechanics derivation of the path integral, we can essentially split this time interval into multiple parts, and at each point we can insert a resolution of identity. And through this, what we would end up doing is we would first end up deriving the phase space path integral, where we both integrate over fields and the conjugate momenta. And importantly, when we do such a derivation, we end up with this kind of flat Liouville measure. So correspondingly, this is like formally this is how we'll denote the measure for these fields in the path integral. So the usual thing one does to actually derive the final form of the configuration space path integral is that now we perform the Gaussian integral over momenta. And what we find through this is the usual path integral that we used to, but importantly, we can formally derive an explicit functional measure where we kept track of this determinant of the spatial metric and the lapse in this measure. Now, this functional measure automatically induces for us a natural notion of the inner product on the functional space. This is because you can essentially think of this factor in the functional measure as the volume form on the functional space. And to determine the inner product, you care about essentially the metric on the tangent space to this functional space. So essentially what this boils down to is making use of this relation. And through this relation, you will deduce that the natural inner product that follows from canonical quantization that you would want to use is of this type. So now what we can do is we can compare the inner product that we derived, the symplectic inner product obtained from the canonical quantization with the ultralocal inner product that we considered before. And what we find is that they essentially differ by the factor of lapse squared. Correspondingly, the functional measures also take a slightly different form. So now, naively, what one could think is that, if they only differ by this factor of lambda squared, we could simply redefine our fields, and this should still end up leading to the same answers. Now, this however can be subtle in the cases in which the lapse has some non-trivial behavior at infinity. So in particular, in ADS spacetimes, what happens is that the lapse actually blows up asymptotically. So therefore, in this case, it is not the case that we can simply redefine the fields, because now imposing normalizability with respect to this inner product versus normalizability with respect to this inner product actually leads to completely different asymptotic decays of the fields. So, in other words, what we conclude from these expressions is that in ADS spacetimes, the functional space defined with respect to the ultralocal inner product will differ from the functional space defined with respect to the symplectic inner product. And this is in contrast with asymptotically flat spacetimes, where the lapse does not blow up asymptotically. And therefore, even though there will be some different functional factors in this inner product, the asymptotic decays we would conclude would actually be the same.
Why is it not bothersome that one of these is not covariant?
Right, so that's a good question. So the point is that usually we use the ultralocal inner product because it's manifestly covariant, but at the end of the day, the point here is that it's convenient, but it's not necessary.
Why not?
Because when we do canonical quantization, we also always break covariance. Nevertheless, we would expect that we have just as much covariance in the partition function that we compute through canonical quantization as we would expect in a physical problem.
But in canonical quantization, you're talking about intervals on a spatial slice, and then you check later that the choice of spatial slice doesn't matter. And so
Yes.
here you're talking about the inner product on all of Euclidean ADS. Not quite the same.
It is not the same in this sense, but it is the same in the sense that at the end of the day, this inner product has been derived exactly from a canonical quantization. So if you believe that the canonical quantization is covariant in the way that you would expect, so for example, that the thermal partition function is going to have all of the covariance properties that you want, you can always kind of go back and convince yourself that, okay, the final answer that you derive through this functional methods with this symplectic inner product is going to be the same, because it just follows from these formal manipulations of the canonical quantization. But indeed, you've lost the manifest covariance.
But can you actually check, for example, if you change the slides while keeping the boundary conditions the same?
Mm-hmm.
Can you check that there's a field redefinition that relates in the box?
So that's something that we would want to do more explicitly. But this we haven't yet nailed down exactly what's the kind of the most manifest way of keeping track of covariance in these computations. The kind of a naive a naive argument you could try to give is you could say that usually the changes, like if you do small changes of the slicing, which do not reach the asymptotic boundary, then the kind of canonically quantized fields will be related by some Bogoliubov transformations, or in other words, they're going to be related by some canonical transformations on the momenta and your fields. So then, from this, you could try to say that, oh, okay, it's like you do not need to go all the way back to the starting point. You simply need to go back one step before, perform this change here, and then you see that you end up with the same answer, and then integrate that momenta again. This, however, from what I've learned recently, this is, however, a very subtle argument. This is not necessarily correct because of the subtleties in the phase space path integral. We're still kind of looking for what would be like the best way of keeping track of the covariance in this computation. So going back, we obtained that we concluded that we will obtain a completely different functional space from the symplectic inner product versus ultralocal inner product. And therefore now we can analyze how do normalizable modes behave in this symplectic functional space. So now if we define this the same way as before, but now with the symplectic inner product, and consider the asymptotic decay of a scalar field that this forms into the delta, we're going to find that the normalizability of these modes requires that delta is greater than d minus 2 over 2, which is exactly actually the unit path that we have in ADSP. So in other words, now by changing this inner product to the one that follows from canonical quantization, we actually pushed the allowed region where we can study this, where we can study offshore physics, exactly to the region where we also expect to be able to study classical physics. So now the configurations are part of the integration space, essentially for any choice of boundary conditions that is allowed classically. We are allowed to study the one of the determinants with different boundary conditions now. And furthermore, the analysis of these allowed boundary conditions reduces exactly to the classical analysis that was performed by Ishibashi and Wald.
Actually, even in the flat space case, I mean, people say with entanglement entering so on often do like, radial quantizations, like simultaneous like angular evolution, in which case like the lapse would be growing like R squared, growing like R. So it seems like there might be an issue there.
So you mean if you just study flat space case, but within radial quantization?
Well, where the Hamiltonian is then the when you go to Euclidean, the Hamiltonian you do the rotation operators. Things people do when they derive the entanglement, you do the half space. So just using a different Hamiltonian, using maybe Renzi using the generators and Hamiltonian.
Are you referring exactly to like the subtleties about the fixed point?
Well, there's the fixed point, but there's just also the growth of the growth of the lapse in those coordinates of large R, so you have the same same tradition.
That's a nice point. I hadn't thought about this in this context, but it sounds like it should the same kind of issue would appear. Yeah. Thank you. So now, since we changed the inner product, what this means is that now when we want to reinterpret this expression in the exponential as some operator acting on this Hilbert space of fields with respect to this new inner product, we actually have a modified definition of the operator that we want to diagonalize. So now, because of this factor of 1 over n squared appearing in the symplectic inner product, we have to correspondingly insert this factor of lapse squared in front of the Klein-Gordon operator. This has nice consequences because now the Klein-Gordon operator will exactly take the same form as kind of the Klein-Gordon operator that you would end up studying classically when you want to study classical physics. Because there, if you actually solve Klein-Gordon equation on the right-hand side of these equations, you have 0, so we can always divide by the factor of lapse that would appear in front of the time derivative. So what this means is that now when we want to study the spectrum of the operator, the thing that we care about the most is diagonalizing this operator A hat. But this operator A hat is exactly the same operator that you diagonalize when you just study classical physics. And so in particular, this is the same operator that was studied by Ishibashi and Wald, and the whole analysis of the allowed boundary conditions for this operator goes through in this offshore case now. So this already implies that we're going to have the same boundary conditions for offshore and onshore physics, and that for any of the choices of these of the boundary conditions, we're going to end up with a discrete spectrum for the Klein-Gordon operator now. So not the discrete spectrum of energies, but even the discrete spectrum of eigenvalues for this offshot problem. So to recap, one can now, for this operator hat, one can now study its spectral properties, and one would again find that for large enough masses, the operator is essentially still adjoint and only admits Dirichlet boundary conditions. However, for the masses in this BF window, the operator is only symmetric and therefore admits some self-adjoint extensions. There's this one parameter family of boundary conditions, which are the mixed boundary conditions that we're used to in ABS spacetimes. So now this concludes this analysis of this basic case of the free scalar field, and now we're going to discuss how it helps to resolve some puzzles in these supersymmetric setups. So for this, we're going to consider essentially a chiral multiplet of n equals to 2 gauge theory in ADS3. So the action is given essentially by this expression. So here, pi and pi tilde are the scalar fields that correspond to the respectively chiral and anti-chiral multiplets. F and F tilde are the auxiliary fields of these multiplets, and psi and psi tilde are the Dirac fermions in this multiplet. Now, for thermal ADS3, in those theories can actually be made into a supersymmetric background by turning on some background non-dynamical gauge field A with this specific profile, where tau1 and tau2 are essentially the modular parameters of your asymptotic boundary torus. When we turn on such a background field, this thermal ADS3 geometry will preserve 2 killing spinors. So this is the sense in which it is now a supersymmetric background. And yeah, they're given explicitly for these expressions. And note that they're going to have a very specific behavior near the boundary because of this 1 over sine of x. So in other words, they're going to blow up close to the boundary because the boundary in these coordinates is located at x equal to 0. So now let's review the puzzle discussed by Ashok Sen in the context of this theory. In the paper, it was discussed in the context of ABS2 crosses 2. However, as I was saying, it's a very universal puzzle, so it also holds in the case of ABS3. So asymptotically, these killing spinors blow up as this 1 over square root of x. Now, for ultralocal inner product, all of the eigenfunctions for the Klein-Gordon and Dirac operator, which, by the way, are exactly the relevant ones here, because that's why we started with this theory, because it's particularly simple. Because you can just care about the diagonalizing the Dirac and Klein-Gordon operator to compute the one-loop determinants, because it's already quadratic. The eigenfunctions decay asymptotically this way. So they are precisely kind of these real parts of this coefficient of these exponents are precisely tuned such that these fields are going to be delta normalizing. So in other words, the real parts are actually lying exactly on this point of the axis that we discussed before. So they are kind of on the edge of what's allowed by the ultralocal inner product, and that's why they are not normalizable. They are delta normalizable. Now let's consider applying a supersymmetry transformation onto this on this scalar field. So this supersymmetry transformation will essentially act with this killing spinor on the Dirac field. And so what we're going to find is that if we first started with this delta normalizable scalar field, after applying this supersymmetry transformation, it's going to essentially move the real part of the asymptotic decay to the middle of the BF window. And correspondingly, this means that we have ended up now with a mode that's not normalizable with respect to the ultralocal inner product. So this essentially implies that the space of eigenfunctions that we would want to that we care about for computing one-loop determinants is not preserved by the supersymmetry transformations, and this therefore introduces problems whenever one tries to compute these explicit supersymmetric indices in this series. But now, immediately already from this plot and from our previous discussion, we can expect that okay, now this is just gonna be resolved when we work with this different inner product, and indeed, now with the symplectic inner product, the asymptotic decays are gonna be exactly the same as classically, because now to find the radial part of these eigenfunctions, what we had to do is diagonalize this operator A hat. And so now asymptotically, the decays are going to be exactly the same as classically. And then what this means is that just because of classical physics and the fact that the classical equations of motion are going to be invariant in this theory under supersymmetry transformations, this already implies for us that the space of offshore fluctuations with respect to the symplectic inner product is going to be actually invariant under supersymmetry transformations. And so in this way, we see how how working with the symplectic inner product helped us resolve this issue and allows us now to explicitly compute these supersymmetric indices in those cases. So this was essentially the main upshot. So let me now go to the summary. So what we did in the talk is we essentially compared properties of two natural functional integration spaces that we could consider for studying physics in ABS spacetimes. So we compared with together the ultralocal functional space and the symplectic functional space. So we found that the functional space defined with respect to the ultralocal inner product leads to a continuous spectrum of the Klein-Gordon operator. It does not allow for different choices of boundary conditions, as we would expect from classical physics. And it is not consistent with supersymmetry transformations. On the other hand, after returning to canonical quantization, we found that the resulting natural functional space that we would study from that perspective actually leads to a discrete spectrum of the Klein-Gordon operator, as we would expect from the expectation of ADS acting like a box. It allows for different choices of boundary conditions and is consistent with supersymmetric transformations. So the key point to conclude that these are actually different was the fact that in ADS there's a blow-ups of the lapse factor at infinity. So kind of the key lesson from this is that whenever there are some wild behaviors of the lapse factor in the geometry, one has to actually genuinely ask the question: what is the natural inner product that we should consider that actually captures the aspects of the physics that we're interested in when studying the partition functions. So now for future direction, what we would like to address is extend this analysis to vector fields and the metric, so that then we could actually revisit some of these ADS 2x2 computations. Here we focus only on the chiral multiplet because that was the simplest setup where we could analyze this. There's a natural question of how does it compare with the natural measure used in JT gravity, and whether in JT gravity the usual results are actually consistent with ultralocal inner product or not. And lastly, this should allow us to now formulate more precisely the question of localization in ABS spacetimes, which was in the past ran into some confusions, which one can kind of identify were actually related to this choice of the inner product in those computations. Yes, and so that's all I have for today. Thank you for your attention.
The last point, so okay, the puzzle that Sen brought up was sort of like there was some answer which seemed consistent, but then going back into the computation, you find some confusion, right? Which
Yes.
the results are there are actually cases where the result is not
Yes.
known to be correct or consistent.
Yes, there are actually cases where one runs into enough difficulties that where it was not clear what's the best way to proceed. So there are papers that, for example, propose a few different answers from the index, and it's very difficult to actually. It seems that some of these results lack the missing principle for identifying which result is actually the right one. So the hope is that with this, one can now more carefully look at these computations and actually formulate the localization computations slightly more rigorously in ADS systems.
In some computations, with an ADS, you have to do holographic normalization where you actually put in a finite cutoff first on the space. You define boundary conditions on the finite cutoff, and then take the cutoff away at the end.
Yes.
You did that here using the two choices of measure. You still think those would give? So there, each one is well defined when the cutoff is finite, but
right.
I think they would disagree.
Right. So the funny thing is that if you use the ultralocal inner product at finite cutoff, and then take off the cutoff, you're gonna find that the answers are consistent with the symplectic inner product, but not with the ultralocal inner product without the cutoff.
Okay, so I see. So you can put in the cutoff, take it away, then you're fine.
Yeah, exactly. Yes. But on the other hand, you will not be able to actually do analytically much progress. Like to actually compute these, like diagonalize this operator at finite cutoff and keeping track of all of these finite cutoff effects. That will be a very challenging computation. That's why we usually like to work directly with asymptotic, with this cutoff being at asymptotic infinity.
Other questions? All right, let's thank Jan for the great talk.